Good afternoon, everyone. Am I audible? First, thanks Ajith and the other organizers for allowing me to take part in this really wonderful meeting in honor of Bala. And Bala, thank you for being an inspiration to us all. I really hope that we can keep the fire burning going along. So today I have a rather unusual goal. So my first order goal is to tell you all, astrophysically speaking, what we know well and what we do not know well. And many of you probably know this, but I would like to remind you, okay? Because it seems like there is sometimes a disconnect between astrophysicists and gravitational wave folks. Gravitational wave folks like to learn about the expected rates, and we provide them, but oftentimes what we do not tell you, it's all our fault, what are the uncertainties and how much the rate can vary depending on our lack of knowledge, okay? So let's go on. So this is roughly the outline. So I will talk about the various formation channels. I will not go into much details of the other ones apart from the dynamical formation. And I will just focus on the inherent uncertainties. And I will talk about dynamical formation channel. And I will try to be very, very pedagogical so that you all understand what are the key aspects and what we know very well. And then only when I must, really, really must, I will show you some results that come from detailed simulations. I will not go through take a deep dive in the details of the simulations, but if you ask me, I will oblige, okay? And then I will end with some burning questions. Well, burning questions according to me, okay? All right, so the easiest in terms, well, at least in principle, the easiest way to form two binary black holes is you start with two high mass stars, both of them become black holes, both of the binary is not broken, and they merge. The critical stage is here. So high mass stars can be very big. If you want them to merge only after both of them have become black holes, you need to keep them well separated. And then for the black holes to merge, you need to shrink the orbit by about 3 orders of magnitude. And the way we do it, or we claim that it happens, is through common envelope evolution. So without this magic, this channel cannot work, okay? Unfortunately, this is the least understood stage of binary evolution. Not because of lack of trying, it's just not really as hard to solve. And it has two important parameters, alpha and lambda. And if you play with these alpha and lambda values by a factor of a few, the rates and properties and everything can dramatically change by orders of magnitude, okay? So there is another variety of creating binary black holes in isolation, and that is, what if the high mass stars never become very big? So there is this so-called chemically homogeneous evolution. So you start with two high mass stars, they rotate and do not become giant branch, etc. So you can start them pretty close to each other. They both become black hole, they merge. This channel typically tends to create equal mass, or Q equals very close to 1 type of binary black holes. And I think some of the low Q detections already will have trouble, this channel will have trouble making them. A completely different method is the so-called dynamical formation that happens in dense stellar environments. So this is the key aspect of dynamical formation. So you start with a bunch of stars, they have different masses, and of course the key piece of physics that drives evolution of star clusters is two-body relaxation, and the natural outcome of two-body relaxation is mass segregation. So if you start with black holes and stars well mixed, black holes being more massive come to the center, and then they start interacting with each other. What are the timescales? So the relaxation time scale for typical globular clusters is about 1 billion years. The age is about 10 billion years. And the mass segregation time scale is about 1/10 of a relaxation time scale. So these mass segregation episodes are happening hundreds of times over the age of a globular cluster, okay? So now you have collected all the black holes that were created wherever in the cluster and collected them at the center, like in this conference, right? And in this dense environment, these black holes find each other and start strongly interacting with each other, dominated by binaries. And typically, these interactions are so-called resonant type interactions, where all of these bodies come repeatedly close to each other. And these are extremely chaotic encounters. And oftentimes, you get exchange interaction. For example, this was an exchange. There was a red-red binary came in, red-blue binary went out. Typically, these interactions are super elastic. So you shrink the binary orbit, and the excess energy is carried out by the other star. So what happens? So black holes sync, they interact, and there are 3 ways they can make binary black holes. One is via exchange encounters. So if you start with 2 main sequence star, let's say, another black hole comes, black hole being more massive, exchange it into the binary. Now you have a black hole main sequence star binary, and then another black hole comes and exchanges into the binary. Now you have a black hole binary. So independent of where you formed the black hole, whether or not the black hole was initially in a binary, you have successfully created a black hole binary, okay? There is another channel that is 3-body binary formation. So 3 black holes come just by fluke close to each other. You form a black hole binary, another black hole is ejected. And the other is gravitational wave capture. That's actually very interesting, you will see later. So because of these resonant encounters, black holes can come very, very close to other black holes. And that can generate bursts of gravitational wave energy, and that can release enough energy to make the 2 things bound. Okay? And then once you have formed a binary black hole, the orbit keeps shrinking through superelastic encounters, and until you eject the binary black hole through recoil. Which encounter? The rate, yeah. Oh, this happens all the time, and not only with black holes. It is happening for everything. Yeah. Only a small fraction of these things end up merging. Yes. We're working on it. Okay, so now the properties of these binary black holes created this way depends only on the dynamical properties of the star cluster and almost nothing else. I will tell you why I say almost. And let's go to college physics, okay? So remember, the velocity dispersion is related to the mass and compactness of a cluster, and the escape speed is also related to the mass and the compactness of the cluster. Which binaries survive in a cluster? The binding energy must be greater than the typical kinetic energy of the incoming stars. Which binaries get ejected? The recoil speed, which is typically of order the orbital speed of the binary, must be greater than the escape speed, okay? So you know the range of binaries you can create and retain in a star cluster. And actually this is such a well understood process that, oh, and by the way, the orbital speed of course dictates the separation and spiral times, etc. So this is such a well understood process that this was the solution of a final exam that I have given to my class, okay? So all I told them that find out the range of masses for clusters that are very efficient in creating binary black holes that will merge within a Hubble time. And all they had to do was calculate the time scales. So this is the mass segregation time scale. If you have very large mass cluster, it doesn't mass segregate quickly enough. And then if you have a very tiny cluster, then it cannot shrink the binary enough. So the competition between these two time scales already tell you that roughly about the globular cluster mass range is very efficient in creating these binary black holes that would merge within a Hubble time. And of course, nothing in real life are these well-defined straight lines. So let me show you some real simulation figures. So here I'm showing you the cumulative distribution of in-spiral timescales for different masses of clusters. And this shaded region marks Hubble time, okay? So you can see that these are the typical numbers of globular clusters. Not only the globular clusters are very efficient in creating these binary black holes, the most efficient globular clusters are also the most numerous in nature. So it's as if nature has created globular clusters to create binary black holes, okay? So there are a few consequences. The merging binaries are not primordial, right? So there goes all the uncertainties about what we do not know about binary initial conditions, common envelope, etc. Black hole spins are randomly oriented relative to the orbit because you are always assembling them through dynamical processes. You expect high eccentricity during formation, but that eccentricity can decay before it reaches 10 hertz. But during gravitational wave capture, it can actually form at 10 hertz. And then you will see very high eccentricity. And probably the most exciting is the so-called second generation merger. So you can form a binary black hole, the two black holes merge. The merger kick was not high enough to eject it from the cluster. And then this black hole is more massive than all other black holes in that cluster. So this will very quickly get itself into a binary, acquire another black hole, and merge again, okay? So we call that second generation merger. And of course, through second generation merger, you can, even if the Barth spin was low, the merged product will be spinning very fast. And also the mass of the second generation black hole will be potentially higher than the limiting mass you expect from stellar evolution, okay? So here are some results. These, the rows denote different assumed Barth spins for the black holes. This is for all redshifts, local universe, and this is the detected distribution. So let's focus on this column. The blue is 1G plus 1G, orange is 1G plus 2G, and green is 2G plus 2G. So you can see that if the Barth spin distribution is very small, you can have a significant number of 2G plus 2G mergers, and they will be very easy to know because if there is a limiting mass in black holes, then they will definitely be above that limiting mass. There are these 1G plus 2G, and the 1G, 1G ones end here. So anything above this mass will be a telltale sign of dynamical formation. Oh, the dots are, these are the LVC detections, and these are the new IAS ones, okay. This is the chi-effective distribution. Again, the same, the columns and rows mean the same. So let's look at here. So of course, if the Barth spin is 0, then 1G, 1G will be all 0 by definition. And then this is 1G plus 2G, 2G plus 2G, etc. And the really nice thing about this is if the Barth spins are close to 0, then you keep more and more these second generation mergers, and that spreads the chi-effective distribution. If the Barth spins are large, then it's spread out anyway, right? In that case, because they are spinning by birth, the after merger kicks are also very large, so you don't get as many second generation mergers. So we are still yet to know which one is more true. Let's look at the eccentricities. So this is at 10 Hz. So the first generation are the blue. Orange is the one plus, oh no, this actually has different color scheme, I'm sorry. So there are these mergers that merge after they are ejected from the cluster. That's the blue. The orange is in-cluster mergers. These are the ones that can hope to create a second generation. And the maroon is gravitational wave captures. So you can see that the captures can have pretty high eccentricity even in the LIGO band. And of course, if you go to LISA or DECIGO, so basically lower frequencies, all of these in-cluster and ejected mergers can have detectable eccentricities at lower frequencies. I'll skip this. So these, I think, are the burning questions. So the retention fraction in black holes in globular clusters have had a very long and checkered history. We thought that black holes don't exist in globular clusters, then we thought it doesn't, and so on, back and forth. I think we now understand it very well, but we need to measure these things, and our group has started doing it systematically. Then the black hole Barth mass function, black hole Barth kick distribution, and common envelope evolution, we don't understand much. So there are prescription-based models, and we use it almost blindly believing in them, but everything can change simply by changing any of these knobs of these prescriptions. And the only way, I would say, so there are indirect evidences that can be found to find out what is the present number of black holes in clusters. And this needs large number of detections, and maybe someone will ask me questions during the discussion. I would argue that Gaia may be instrumental in providing this large number of detections. Thank you.
Thank you.